Hey everyone, imagine training models that learn patterns we can't even see today, or solving optimization problems in minutes that now take years. Today, we explore how quantum computing could completely reshape AI's future landscape. Stick around. By the end, you will know what quantum AI is, why it matters, and how to get ready. I am a tech creator who loves breaking down complex systems into actionable insights. And today we'll move from core concepts to practical implications. What's a qubit? How quantum differs from classical computing. The specific ways quantum can accelerate AI, real-world use cases, current limitations, and how you as a developer or researcher can prepare. Ready? Let's dive in.
First, quick foundations. Classical computers use bits, zeros and ones. Quantum computers use qubits, which can be in superposition. Think of a spinning coin that is both heads and tails until you look. Qubits also entangle, creating correlations that don't exist classically. Two fundamental consequences: exponential state spaces and fundamentally different operations. Important note, having more qubits doesn't automatically mean better results. Coherence, error rates, connectivity, and algorithm design matter hugely. So what's the difference in computation? Classical algorithms manipulate bits deterministically. Quantum algorithms manipulate probability amplitudes using unitary gates. Interference lets us amplify correct answers and cancel wrong ones. Practical consequence: certain tasks have proven quantum speedups, like factoring, Shor's algorithm, or searching unstructured data, Grover's algorithm. But for many everyday AI tasks, the speedup isn't automatic. We need algorithms that map machine learning problems to quantum-friendly subroutines. Now the key question: how can quantum computing help AI? There are a few major pathways. 1. Quantum-enhanced optimization. Many ML problems boil down to optimization, and quantum annealers, or variational quantum algorithms, can explore complex landscapes differently. 2. Quantum linear algebra. Algorithms like HHL propose exponential speedups for solving linear systems, which is central to regression, kernel methods, and parts of deep learning. 3. Quantum feature spaces. Quantum states can represent extremely high-dimensional feature maps, enabling new kernels for classification. 4. Hybrid quantum classical workflows. Near-term usefulness likely comes from combining classical neural networks with small quantum modules, QNNs, variational circuits, to offload specific subroutines. Use concrete example. Imagine combinatorial architecture search or portfolio optimization inside model training getting accelerated. Let's unpack algorithms. Variational quantum algorithms, VQAs, like VQE and QAOA, are leading near-term candidates. They use a parameterized quantum circuit and classical optimizer together. These are promising for optimization and even for training quantum neural networks. There are also quantum subroutines like amplitude estimation, Hamiltonian simulation, and quantum singular value transformation that could underpin faster linear algebra and sampling. Pro tip: currently it's about finding problem kernels where a small quantum routine provides outsized benefit inside a mostly classical pipeline. Where could this matter in the real world? A few promising application areas. Drug discovery. Quantum simulations of molecules can make lead identification faster and more accurate. Materials science. Modeling electronic structure for batteries or catalysts. Combinatorial optimization. Logistics, supply chain, and scheduling problems that plague large-scale ML systems. Advanced ML tasks, kernel methods, feature engineering, and possibly faster inference or training for special architectures. I want to be clear, most of these are exploratory today, but several pilot projects in industry and academia are showing real potential. Don't get carried away. There are big challenges. Current quantum hardware suffers from noise, short coherence times, limited qubit counts, and high error rates. Many quantum algorithms require fault-tolerant machines, which may be years away. Mapping ML problems to quantum circuits is non-trivial and can introduce overhead that cancels theoretical speedups. Finally, data input and readout. loading classical data into quantum states and extracting useful information is a bottleneck. Where are we now? We have noisy intermediate-scale quantum, NISQ devices from multiple vendors, and cloud access to small quantum processors and simulators. Active research areas, error mitigation, scalable qubit architectures, hybrid algorithms, and software tool chains. Roadmap expectation, near term, 1 to 3 years, hybrid experiments and niche advantages. Medium term, 3 to 8 years, more robust error mitigation and larger circuits. Long term, 8 to 15 plus years. Fault-tolerant quantum computers enabling broad algorithmic breakthroughs. How can engineers, data scientists, and researchers prepare right now? Here are practical steps. 1. Learn fundamentals, linear algebra, quantum mechanics basics, and quantum information concepts. 2. Get hands-on. Try cloud quantum platforms, IBM, Rigetti, IonQ, Amazon Breakit, and simulators. Build small variational circuits and integrate them into classical workflows. 3. Focus on problem framing. Identify small kernels in your stack where quantum subroutines might help. Optimization, sampling, kernel evaluation. 4. Participate in communities and open source projects to keep pace with tooling. Quick visual explainer demo idea you can recreate. Implement a tiny variational quantum classifier in a simulator. Conceptually, encode two-dimensional data into a pair of qubits using angle embeddings. Run a parameterized layer, measure and map to a class label, then use a classical optimizer to update parameters. This demonstrates hybrid training loops and helps you understand gradients, measurement noise, and parameter landscapes firsthand. Before we close, quick real examples to watch. 1. Pharmaceutical companies partnering with quantum startups to simulate molecules. 2. Logistics firms testing QAOA-like approaches for routing. 3. Research teams publishing hybrid ML plus quantum experiments showing potential gains on carefully selected benchmarks. These are early, but they highlight where value first appears. Looking forward, expect quantum computing to become another specialized tool in the AI toolbox rather than a universal replacement. The most realistic near-future outcome is a hybrid ecosystem. Classical deep learning for general scalable workloads, quantum modules for specific subroutines that need exponential expressivity or novel optimization strategies. If hardware and algorithms keep improving, we may see new classes of models and training techniques that are impractical today. If you found this helpful, smash that like button, subscribe for more deep tech explainers, and comment below. What quantum AI topic should I build a hands-on tutorial for next? I read every comment, and I love building community projects with you all. Also, check the description for resources and starter links.